Hello, so today I want to talk about my Data Structures 2 course project, which was worked on by me, Sara Baloch, Musab, and Musab. And we focused on implementing a data structure called dynamic trees as per the implementation detailed in a paper from the 1980s by Sleator and Tarjan, the same Tarjan that introduced the strongly connected components algorithm. Now what this data structure does is that it allows us to represent any tree, regardless of how imbalanced it may be, in such a way that we can carry out all of these operations in logarithmic time. Now some of these operations are a bit simple, like finding the parent of a node or finding the cost of an edge connecting a node to its parent. But we also have some more interesting operations which should really take more than logarithmic time, just from a naive implementation, such as min cost of v, which considers the path from a node to its root, to the root of the tree, and finds the cost of the edge on that path with the minimum weight. Now maybe you'd want to search every edge, but this implementation optimizes on that. And another thing to note is that this data structure doesn't work for a single tree, it actually works for a forest of trees, hence why it's called trees, as opposed to just dynamic tree. And the way that works is you also have these two operations called link and cut, where link allows you to connect two trees via an edge to become a larger tree, and cut allows you to remove an edge from a tree to separate it into two smaller trees. You can also change the root of the tree, update the cost of the edges of the tree, and just find out the root of any specific tree, all in logarithmic time. Now, how do we reach these optimizations? Well, we need to break down our implementation into two main parts. So the whole tree can be represented with some dashed edges and some bold paths. Now the dashed edges are very simple. It is a simple hash map from, for example, G has a dashed parent of B, C has a dashed parent of A, and E has a dashed parent of A. But you also have these bold paths which allow us to travel really fast up the tree by just having we can have global or range based values for the whole tree, which can allow us to traverse the tree much faster by jumping up these bold paths. Now the bold paths themselves are actually represented via binary trees. So if I had a bold path from nodes A, B, C, D, and E, where E would be higher up in the tree and A lower down, then the binary tree representation of this would be as shown, where each of the internal nodes is actually representing an edge in the tree, and the external nodes, the leaves, represent the actual nodes in the tree, nodes in the original tree. Now the interesting thing is that if I do an in-order traversal of the binary tree, I will get back the same order A, B, C, D, E as of my original path, where A is considered the head of the path and E is considered the tail of the path. A small note to make here: if I consider the path ABF, actually the head of this path is the one which is lower down, which is F, and the tail is the one which is higher up, which is A. Now talking about complexity again, we see that everything is logarithmic in time here. But if we just took a more naive solution, for example, we just represented the entire tree with dashed edges, then we could do a bunch of operations in order of 1 time. However, there are some which would take order of n time. The benefit of the dynamic trees implementation is if you need to actually mix both of these fast and slow operations a bunch, then having all of them be logarithmic in time actually speeds things up. And we'll see an example of that in just a second, applied to network flow. Now, if we go one layer deeper into how this all works and how the optimizations work, there are two key operations that go into it. One is called splice and the other is called expose. Now splice takes in a path, a bold path, and it extends it across one dashed edge. So for example, if I had this path P, currently it stops here. Keep in mind that the tail is the one which is higher up, and it stops here, and then there's a dashed edge to V. What a splice will do is it will replace this dashed edge with a bold edge. Now our path is extended. However, if we just did that naively, then V would be part of two bold paths, one from P and then one from Q. So we need to convert the edge connecting V and Q into a dashed edge. So splice will do that. Now what expose does, it just repeatedly applies splice until path P is extended all the way to the root of the tree. Right? So if I started from here, and actually expose takes in a vertex, not a path. So that's also a small difference, but you'll see that, okay, if we start with V, after expose there will be a clear bold path ending, or sorry, starting from V and ending at the root of the tree. Now for the actual nodes in the binary tree, we have to store many different details. So we store the simple left and right pointers and the parent pointers, but other than that we store head pointers and tail pointers, where the head is the the first node in the in-order traversal and the tail is the last node in the in-order traversal. Then we also store these metrics called net cost and net min, which help us across various operations, and so they're defined a little bit different than what you'd expect, and the details of that are in our report and also in the paper itself. So I won't go into that right now. And other than that, you can store whether a path is reversed or not. So if I set this bit here to 1, then this would mean that this whole path is reversed. And this can be handy, for example, in the evert operation, which changes the root of a tree. So I might want some of the edges which were below me to still stay below me, but some of the edges which were above me may have to be reversed so that they all point towards me. So that's where the reversed bit comes in handy. Now let's sort of look at the actual data structure in action. So we have an implementation here and a visualization. So let's look at a sample tree which we have on our right. And for this tree, this weighted tree, the internal representation of this would be like this. So we have a bunch of dashed edges and we have a bunch of bold paths. Now a key thing to note here is that every node, even if it's not seen to be part of any bold path, it is actually part of some bold path, perhaps of length 1, right, just containing the node itself. As for this other path, so you have a path from 6 to 4, so this is represented by this big tree, where this represents edge 2,4, this represents edge 6,5, this represents edge 5,2, and if we did an in-order traversal of this, then this is a little bit interesting because our head is now pointing to 6 and our tail is pointing to 4. But I said the head is the one which is lower down and the tail is the one which is higher up. The reason why this is happening is, look at this star here. This star means that this subtree has been reversed, which is why 6 is now the head and 4 is the tail internally. Keep in mind that this is all internal. Now I can apply some operations. I think my favorite is cut. So let me try to cut. So cut will remove an edge from the node and its parent. So maybe I can try cut 4. And this will give me 2 new graphs. So this will give me 2 new outputs. One is the actual tree, so we'll see that the path from 4 and below has been separated, and we'll see that we still have the path from 6, 5, 2, and then 10, and then 7, so that's all maintained. And yeah, also there are these numbers over here which represent the bias of the nodes in the trees. And the bias actually helps in making sure that these operations all happen in logarithmic time. There's some balancing which is done intelligently through using these numbers, and again the details of that are detailed in actually a separate paper by Sleator and Tarjan, which we had to go through, but yeah. And you can see how the different operations sort of work, and maybe let me try one more. Min cost. Let's say if I wanted min cost of 8, so this should give me 1 because the path from 8 to the root, which is 4, has 1. So if I do min cost of 8, its result is 3 because 3 is the vertex which has the min cost edge coming out of it, right? So the output is the node. And then from the parent of that node I can determine, okay, this was the minimum edge. Alright, so that's a visualization of some of the operations. Jumping back into it, to actually get all of this to work, there is a lot of underlying helper functions, which again detailed in the report. And now let's get to an example of where you might want to use this. Now, one very powerful example is network flow, where we want to find the maximum flow that we can have from a source of a network to a sink. A typical algorithm might be Ford-Fulkerson, but then there's also this algorithm called Dinix algorithm, and dynamic trees optimizes the Dinix algorithm further. Now, the network flow algorithm is very useful whether you're dealing with transportation, whether you're trying to send packets across a internet network faster, or whether you're trying to just schedule a project, or many other applications. And so again, a very typical approach is to use the Ford-Fulkerson algorithm. Now this has a complexity of v times e square. However, there's also the Dinix algorithm, which has a complexity of e times v square. I think it should be v square, my bad. But so you can either have v times e square, or you can have e times v square. So there will be, for sparse graphs, for Fulkerson will be faster, but for dense graphs, Dinix would be faster. And so when we actually run the algorithm, and here's some details about the Dinix algorithm, but if we actually run the analysis, so if we have a very sparse graph, then we see the Dinix algorithm without dynamic trees actually takes a lot of time. Whereas if we use the dynamic trees, and then there's an optimized version of the dynamic trees, which the difference is detailed again in the report, but we'll see that, and very funnily, the optimized version takes longer than the default version, and that's because the edges are connected randomly, so there's no further need to optimize. But if they weren't connected randomly, then you have cases where actually the optimized tree is better to use. But we see that in this very sparse graph, our implementation using dynamic trees is faster than Dinix, but not faster than Ford-Fulkerson. So let's try a more dense graph. So if we have a more dense graph, then Ford-Fulkerson blows up, and our algorithm still somewhat maintains itself and stays, like, it performs better than Ford-Fulkerson. So we're really happy with those results, and we have a lot of details for how we really pull this off, our understanding of the whole data structure broken down bit by bit, for if you're interested, and along with some of the errors maybe we found, or corrections that we at least had to do in our code as compared to what's detailed in the paper listed here. But would really appreciate if you can read the paper, and would definitely recommend checking out the original paper by Daniel D. Slater and Robert Andre Tarjan, and their other paper on biased search trees, which actually help this optimization really kick in. But yeah, that was the project. Thanks for listening, and I hope you enjoyed.